Hi, welcome to a new chapter. This is a chapter on exponents and logarithms and exponential and logarithmic functions. And to introduce the whole idea of exponents and exponential functions, I've got a few examples for us to play around with. First of all, here's a big list of numbers. So these black numbers here have a special property. You can take any two numbers on this list, multiply them together, and you'll get another number on the list. If you want to, pause the video and try this out for yourself. Pick a couple numbers on the list, multiply them together, and see if what you get is also on the list somewhere. Okay, I'm going to try an example. I'm going to pick out, 243 and 59,049. I'm going to multiply those together, 243 times 59049. And the answer is 14,348,907, which is on the list. The little blue numbers on the side just help us refer to these numbers. So the fifth number times the 10th number gave us the 15th number. Okay, the reason this works and what's special about these numbers is that they are all powers of 3. You've got 3 to the first power, 3 to the second power, 3 to the third power, and so on. So when I multiplied together the 5th and 10th numbers on the list, I was multiplying together 3 to the 5th power times 3 to the 10th power. That is 3 times 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 3. So altogether, that was 15 threes multiplied together, 3 to the 15th power, which was the number on the list at position 15. So not only can you multiply two numbers on this list together and get a number on the list, you know which number you're going to get because you can add these two little blue numbers together to tell you which product you're going to get. And these little blue numbers are the powers or exponents that 3 is raised to. And we could also say that they are the logarithms, the base 3 logarithms of these numbers. It's going to be a little while before we officially start talking about logarithms, but just as a preview, what logarithms are, they are exponents. They are the powers that you have to raise a number to get another number. So when I say that the base 3 logarithm of 243 is 5, I'm saying that 5 is the power that you have to raise 3 to end up with 243. Here's another list of numbers that has that same property. You can pick any two numbers on this list, multiply them together, and get another number on this list. Again, pause the video if you want to try this for yourself before I show you an example. But if I take 2048 times 4096 and multiply those numbers together, the result is 8,388,608. That is, well, these numbers are powers of 2. 2 to the 1 power, 2 to the 2 power, 2 to the 3 power, and so on. So what I did was I multiplied together 2 to the 11 times 2 to the 12, and I got 2 to the 23 power. There's a general rule or property of exponents that says that a to the m times a to the n equals a to the m plus n. When you're multiplying two expressions together that have the same number to different powers, you just add those powers, those exponents. Now, another thing we could do with this list of numbers is we could divide. We could take any two numbers on the list and divide, and we always end up with another number on this list. For example, let's try 171,072 divided by 16,384. So 131072 divided by 16384, and the result is 8, which is a number on the list. What I just did was I took 2 to the 17th power and divided it by 2 to the 14th power. I took the 17th number on the list divided by the 14th number, and I got the third number on, and I got, wait, did I? Yes, I got the third number on the list. Sorry, I had to go in and fix my equation. What if we did, well, what if we did 8 divided by 512? So they were doing a smaller number divided by a bigger number. 8 divided by 512. And we get a decimal, 0.015625, which doesn't show up on this list of numbers, but what it ought to be is, if you take 3 minus 9, you get -6. So what 8 divided by 512 ought to be is 2 to the -6 power. And if I include some more numbers on my list to allow for negative powers, 2 to the -6 power is indeed the number we got when we divided, 0.015625. Notice the pattern here. 2 to the 0 power is 1. 2 to the -1 power is 0.5, which is 1 divided by 2. 2 to the -2 power is 0.25, which is 1 divided by 4. 2 to the -3 power is 0.125, which is 1 divided by 8. It's 1 over 2 to the 3rd power, and so on. So that's the pattern for when you have negative exponents. Now, a couple more examples of exponential functions. So this example has a famous story or legend or situation that goes with it about the origin of the game of chess. Supposedly, according to the legend, when the inventor of the game showed it to the Emperor of India, the Emperor was so impressed by the new game that he said to the man, "Name your reward." "O Emperor, my wishes are simple. I only wish for this. Give me 1 grain of rice for the first square on the chessboard, 2 grains for the next square, 4 for the next, 8 for the next, and so on for all 64 squares, with each square having double the number of grains as the square before." The emperor agreed, amazed that the man had asked for such a small reward, or so he thought. After a week, his treasurer came back and informed him that the reward would add up to an astronomical sum, far greater than all the rice that could conceivably be produced in many, many centuries. So if you really do double the number of grains of rice from one square to the next, here's what the numbers look like. As you go across the first row, you have 1, 2, 4, 8, 16, 32, 64, 128, then 256, 512. By the time you're at the end of the second row, you're up to 32,768 grains of rice. Keep on doubling, and about halfway through the next row, you're up to 1,000,000. By the end of that row, you're up to 8,000,000. By the end of the next row, you're up to, well, in these little tiny numbers down at the bottom, it says what the actual number is written out. And by the time you get to that very last square, you get a number that starts with a 9 and has 18 digits after it. So yeah, that is a really astronomical sum. There's no way you could gather up that much rice. So this is an example of what we call exponential growth. The grains of rice keep doubling. And this is an example that I always use when I start this chapter. But as I'm recording this, we are, of course, in the middle of a coronavirus pandemic, and that makes the idea of exponential growth all too real. If you think of not grains of rice, but number of people infected with the coronavirus, and think of that number doubling every so often, if it doubles, say, every week, then, and actually it's faster than that, but let's just say the number of infections doubles every week, which would be what would happen if each infected person just infected one other person. Then at the end of 8 weeks, you'd have 128 people infected. At the end of 8 more weeks, you'd have 32,768 people infected. At the end of 8 more weeks, you'd have 8 million people infected. And it couldn't go on like that forever because worst case scenario, everybody in the world gets infected and then there's no more infections after that. So there is an upper limit. But if it really does follow exponential growth, where the number of cases doubles every so often, eventually it's going to be growing very, very rapidly. Okay, here's my other introductory example. The population of Happy City is now 100,000 people, but it's growing at a rate of 3% per year. So 1 year from now, if it grows by 3%, that means we add on 3% of 100,000, which brings it up to 103,000. And then 2 years from now, we add on 3% of 103,000, which brings the population up to 106,090. So at first it looks like it's growing by just around 3,000 people a year. What would it be 20 years from now? Well, if it really did just grow by 3,000 people a year, then in 20 years it would have grown by 60,000 people. But that's not exactly what's happening. Here's the chart showing the population from year to year if it really does grow by 3% each year. And the thing is, the bigger the population gets, the more of an increase you see. 3% of a big number is bigger than 3% of a smaller number. So really what's happening is that with each year that goes by, you add 3% of the previous year. Or another way to look at it is you take 100% of the previous year's population plus another 3% of that. So adding 3% is the same as multiplying by 103% or 1.03. And if we do that once each year, then at the end of 20 years, the population is going to be the starting value of 100,000 times 1.03 for each year that goes by. So 1.03 to the 20th power. Okay, I'm going to stop this video right here, and then we're going to get into some of the details, the algebraic and analytic and formulaic details of exponential equations when we pick this up in part 2. See you there.